Okay. Let's start with today's lecture. Basically, let's try to recollect what we did in the last class. Okay. Last class, so the class before that, we started out with distillation with reflux. We defined what does the diagram look like, what does the setup look like, and after that, in the last class, what we looked at is special case scenarios. What if we took the top off? What if we took the bottom off? What if we have a partial condenser instead of a full condenser? What if we took a side stream from one of the plates, like a liquid side stream? What if, instead of the boiler, we had steam injected to heat up? Okay? So we looked at many different scenarios. I gave a problem, or I was discussing a problem, and I told you guys to go and work it out, or give it a shot. This problem was a stripping column with direct steam injection. Hopefully, I will discuss a solution, not this particular class, but I'll try to discuss it in the next class, okay? So then, I left off a topic which is called estimation of efficiency of tray and pack towers. Okay? I did discuss one part, which is the Murphy vapor efficiency. Murphy vapor efficiency, or the Murphy tray efficiency as called by your textbook. It tells you how close to the equilibrium can you go, okay, in the vapor phase. That is very important for us to know, because that's when we start transferring all of our knowledge to build McCabe field diagrams, to go from a theoretical point to a real point, okay? Doing a real tower design. In reality, we only have a certain amount of time to contact between the two streams, okay? We don't have infinite amount of time. If we had infinite amount of time between two streams, between two plates, yes, then we could use the McCabe field diagram. But if you have an efficiency, or if you have like a real-time system where the flows don't stop for infinite amount of time, you're going to have to account for efficiency. Efficiency meaning how close to the equilibrium did we get. Okay? So we talked about how we can do this staging based on a pseudo-equilibrium diagram that we draw. Okay? I did not discuss some formulas. So these are basically very quick ways of estimating efficiencies based on molecular properties, viscosity. And so if you look at the PowerPoint slide or the lecture notes online for the last lecture, you will see that those formulas are in there. I'll try to bring that slide again next time, okay? I want to try to cover figuring out velocity and diameter for these towers. Typically, distillation towers are tray towers. They're not pack towers. Commercially, when you try to use it in the industry, you try to use tray towers. Tray towers, we didn't study yet how to find the flooding velocity or the diameter tower. In absorption and stripping, we looked at how to find the flooding velocity and operating velocity, then diameter of the tower for a pack tower, if you remember, right? Looking up those correlation charts, we had two kinds of packings, structured packing, random packing. Today, what we'll look at is how do we figure it out for a tray tower, okay? Whatever we learn today about design of these tray towers, it holds true even for absorption and stripping processes, okay? So if you were to design a tray tower for absorption, you would still use the correlations that you study here, okay? Vice versa. For designing pack towers for distillation, you still go ahead and use that knowledge that you learned in absorption. And that's the reason why the design of the tower diameters is split into two. Is that, guys, let's talk about it slowly over time. Typically, distillation towers are tray towers, and that's why it's put over here. And typically, absorption and stripping, they're not always packed towers, but they're typically packed towers inside a lab, like a pilot scale. And so that's why it's put in the absorption section. And then what we'll do is we'll start talking about another method. Okay? So McCabe field method you already learned on how to figure out the number of stages and everything. But there's another method. It's called the enthalpy concentration method, or also called the Pumpkin-Savret method. Okay? So I'll just introduce that like the fundamentals on how to read enthalpy concentration charts and everything. But next particular class we'll do a full hands-on problem solving in class. Okay? All right. Let's talk about a few conditions that often happen in a tray tower. Okay? One of them is weeping. So what is weeping? So the vapor flow rate, weeping, crying, similar to that. So drops are falling. Drops are falling from where? Well, drops could fall through the seals of the trays. Okay? So when does that happen? That happens when the vapor flow rate is too slow. Okay? And so liquid is now falling through the tray. That's not a good condition. That means you need to up your vapor velocity. Okay? So what would you do if you want to increase the vapor velocity? This is a very practical question. Sorry?
Increase the temperature.
Increase the temperature how?
Reboiler or steam.
Good, very good. So steam, inject more steam, or try to increase the power, BTU, you are putting into the reboiler. Okay? Okay. Then comes the extreme condition, where instead of just liquid dripping through the trays, it's actually pouring. Okay? That's called dumping. That's excessive weeping. Okay? Okay. Let me talk about the second condition, which is called downcomer flooding. Sometimes the liquid flow rate is so much high that, not liquid flow rate, sorry. The vapor flow rate is so high and the liquid is unable to kind of pass through easily across the tray. Okay? It's kind of being held back. Hey, let the vapor go through. Such kind of condition leads to backlogging of the liquid into the downcomer or the downspout, along which it's coming down. So that kind of condition is called the downcomer flooding. And so typically the liquid level on the tray above it increases until it reaches flooding condition. Okay, the third type is called the entrainment flooding. Okay, entrainment. Entrainment meaning preventing the gas from flowing through. So for example, you have liquid flowing across the tray and the vapor flow rate is so low that it cannot go across that liquid film or even bubble through it. Then such kind of flooding condition is called entrainment flooding. Okay? This is usually the design limitation. Remember in absorption, it was the gas velocity. In distillation, it's the vapor velocity. Okay? It's usually the entrainment flooding. That's the design limitation. So we'll base all our calculation on this. You see the different scenarios that are caused by excessive gas velocity, low gas velocity. Okay? And so if you put it on a chart, liquid flow rate on the x-axis, the vapor flow rate on the y-axis, you could kind of create a graph. Okay? These kind of show you the transition points between acceptable operation and when you have high vapor flow. Oh, sorry. Let's start with low vapor flow rate. You have low vapor flow rate. Let's say you are operating at this point. Okay? Liquid velocity and liquid flow rate and vapor flow rate. The vapor flow rate starts dropping, then the liquid will start dripping through the plates, and that's called the weep point or the weeping. Excessive weeping starts, and then dumping. Dumping meaning it's just pouring like more than rain. When you start increasing, okay, you start having entrainment. Entrainment means you're now starting to hinder the liquid's flow across the tray. Sometimes, if you're operating at very high liquid flow rates, you can actually accumulate too much liquid on the top tray, and you can have a lot of flooding. Okay. So I hope using this diagram, I've the different kinds of conditions. All right. So for figuring out the maximum allowable vapor velocity, right? We have to figure out the maximum vapor velocity. This small v written in italics with a max symbol, it represents basically maximum allowable vapor velocity. Usually it's given in feet per second. Okay? Then that can be estimated using this fair correlation. Fair correlation says it's equal to some constant read from a chart. Okay? The units of that constant are feet per second. Surface tension of the liquid in dynes per centimeter or millinewtons per meter. Okay, so it's right there. This divide by 20 raised to 0.2. Okay, raw L, which is the density of the liquid, raw V, which is the density of the vapor. Again, raw V is the density of the vapor. Now, does it matter which unit these densities are in? It does not matter because it's the conversion factor. So that's the reason why I didn't mention the density over there. Okay, so now the next thing, let's say for a given system, let's say benzene toluene, you want to figure out the maximum allowable vapor velocity. Well, here you would know surface tension for that system. You can calculate that based on NIST chemistry webbook data. You can, or you can go into lab and calculate that, measure it. You'll know the density of the liquid and the vapor. The only thing that we don't know is this constant read from the chart. So what is this constant read from? Let's look at that chart. Okay. So in this chart, you see K. This is the constant we need to read. Okay. And that's on the y-axis. On the x-axis, this is the flow parameter. Okay? Why is this a flow parameter? Because this L and V, they are in units of mass per time. They are in units of mass per time. So really, think about that equation that we used to figure out the flow parameter in impact time. It was GL by GG times raw V by raw L raised to something. Actually, this is GL by GG only. It's just written differently for tray tops. Okay? So really, this is the flow parameter on the x-axis. And look at the different curves. This is for the 6-inch spacing. So this is for plate spacing. So between two trays, you got to figure out some spacing. Okay? How do you figure out that spacing? Typically, it depends on, and manufacturer specifications will also tell you this. Depending on the diameter of the tray, you select a spacing. Look at this. Or sometimes, the manufacturer will give you a diameter range, saying if your diameter range is in between here and here, you select a tray spacing of this. And these are fixed, 6-inch, 9-inch, 12-inch, or 12 inches is basically a foot, foot and a half, 2 feet, 3 feet. See how it's a little bit of a trial and error method, in the sense you have to first figure out the diameter, then you go back and see if the tray spacing is correct and all that stuff. For the problems in our particular class, we will not go through that kind of iteration. But in reality, you have to go through such kind of iteration. Okay. So, what you would do is you would figure out what tray you're going to use. You will be specified a spacing. So you have to first calculate this L by V ratio or flow parameter. How do you figure out flow parameter? Well, this L by V ratio, GL by GG, you'll have to figure this out. Okay, we'll see how to figure that out in a minute. Because in absorption and stripping it was easy, but in distillation, how are you going to figure out the flow rates of L and V? Right? That's a tricky one. And then you can locate your kV. So for example, if your flow parameter came out to be 0.1, you project it to, let's say we are using a 12-inch spacing, a foot spacing, then you read your kV value. Remember, both the axis, x-axis and y-axis, are logarithmic, so read them properly. Let's try to solve the unsolved problem 1153 and try to understand how can we solve or design diameters. Let me try to break down all the information that Amara read. The very first thing was the very first thing she read was the L and the V's that were given. 19,500 kg per hour. Just double check whatever I'm writing, okay? Then she said the tray spacing is about 2 feet, so that's 24 inches. Then what do we know about the densities? Are we given the density? Yes. Okay. So the density of the liquid is given. How much is that? 673. 673 kg per meter cube, right? Okay. Raw V, which is the vapor density. 3.33. 68. So now we can figure out the flow parameter. So L by V times raw V by raw L raised to 0.2 . Let's see, what values do you guys get?
Is that raised to 0.2 or 0.5?
I'm sorry, 0.5. I am so sorry. Let's raise to 0.5. 0.0687. So let's be precise to 2 decimals. It's about 0.07. Okay. So now, we know spacing, we know the flow parameter. Can we go back to the chart?
Yes. That value might not be.
That value is not correct. It's not. No. 12.56.
12 point?
12.56.
Well, it matches with my previous year's calculation, so can you guys double check?
12.56.
Yeah, it's right. I think it's supposed to be 3.68 over 670. Yeah.
Oh, thank you so much. So it's actually 3.68 divided by 673 raised to 0.5. Now does the value of 0.07 stand okay? Okay, all right. Excellent. Thank you for overlooking my mistake. So if you use this value, locate that value on the x-axis in your textbooks. If you locate 0.07, you'll have to give it a guess roughly. You don't, huh?
It has .07.
Oh, it does. Okay, fantastic. So 0.07, take that and project it all the way to the 24-inch spacing line. So let's say you have 0.07 here, and there are many curves, right? There's one curve that corresponds, I think it's the second last curve from the top, project it all the way to that 24-inch spacing curve, and then read the x-axis, sorry, y-axis value. Okay, let's kind of take a very rough value, 0.35. So now you can calculate the so what do we need? We need Vmax is equal to kV times sigma over 20 raised to 0.2.
Our sigma value is 22.5.
Well, that's given to you.
Yes.
So sigma value is given to you 22.5. What units is it in?
9%.
Great. Sorry, time per centimeter. So then you could just substitute into the formula for Vmax and find out. Okay, this time I'll be very careful putting the values in. I'm sorry. What was your question?
So does the units just work and it happens to come out to be in feet per second, or if we would have used the other value?
Very good question. Very good question. This is how you want to think. So his question was that, so you just plug in the units given and then it comes out in feet per second? It is correct. So basically, what kind, you have to look at it. Is this an empirical formula or is this really a theoretical formula? Empirical formulas really don't care about the units. It is the theoretical formulas where you need to balance the units out. Here, it's an empirical formula. So the units don't turn out correct. So if you really put down, you have to make sure this formula only stands correct if this is in dynes per centimeter, and of course this does not matter. But dynes per centimeter and kV is read from that chart. Then it will be perfectly fine. Okay. All right. So great. Now we have a value. Okay. So what value for Vmax do you get? Sorry, 4.8. 4.8 feet per second. Great. Now, typically, what you do is you have to apply a correction. Okay. So this is the velocity at which the flooding is going to happen. Okay. So this is the maximum velocity beyond which, flooding is just about to start happening. Do you really want to operate at that velocity? No, you'd be safer if you operate slightly lower, right? Now, how do we correct for that? Typically, you apply correction factors, and these correction factors are something like this. Okay. First is you account for the downspout. It's basically, you account for downspout by using a factor of 0.91. or 0.9. Okay. Then you account for what's called the so downspout, meaning this correction corresponds to the following. If you have a tray, it's circular in cross section, you're going to have areas on the two opposite sides of the circle. One is probably for the downspout coming from the top. One is probably the downspout going from to the bottom. Typically, this much area is about 10 to 20, not 20%, 10 to 15% roughly. Okay, so 10 to 15%. So the correlation that we found this was thinking that it is that the vapor is flowing through the whole column or whole cross section. So you have to account for that, downspout area. And hence here I just said, let's say the area is about 10%, downspout area is about 10%, then the downspout correction factor will be 1 minus 0.1. So that's the area neglecting the downspout. Okay. So then, typically you tend to operate in distillation around somewhere between 70 to 80% of the flooding velocity. In absorption, we did it at 50%, the flooding velocity, right? In distillation, you typically operate, so operating velocity is roughly about, let's say here we apply a factor of 0.8, so we account for 80%, okay, times Vmax, okay? So we have to again multiply 0.9 over here, and so this is roughly how we get the operating velocity value. So kindly, can you calculate the value and tell me? 3.5 feet per second, right? Now, let's say we go back to the formula. We know we had to figure out the tower diameter, okay? We had to figure out the tower diameter. We know the flow rate. So if we knew the flow rate of, now this is all calculations of the vapor, right? See right here, these are vapor phase flows, okay? They are not liquid phase, vapor phase flows. So if you take the vapor flow rate, okay, vapor flow rate is in which units? Kg per hour. If you divide it by the density, what is the units of the density? It is in kg per meter cube. And then, so what would you get from here? Your end product, rho over V, that will be meter cube per hour, right? Meter cube per hour. Fantastic. So what is that? That's the volumetric flow rate. One is the mass flow rate. V is the mass flow rate. What you figure out by dividing by density is the volumetric flow rate. If you divided this by the cross section, what would you get? You take meter cube per hour and divide it by meter square, what would you get? Meter per hour, right? So we can write the formula for velocity is equal to 1 by pi by 4 d square. Thinking it's a circle, the area of the circle will be pi by 4 d square. Okay. Now we need this v over rho over here, so we can have meter cube per hour. You see how I wrote it? You don't need to really remember the formulas. You can derive these right from the units, the ones that are based on theory. Okay, the ones that are empirical, you got to remember them or look them up. Okay, great. Let's apply this knowledge and try to calculate d square. Okay, so d square, how do you find that out? V divide by, 4v divided by pi rho the small v. Okay, this is the operating velocity. Everybody following so far? All I did was just kind of manipulate this so I have d square over here and bring down the... That's it. Go ahead and calculate this. You have the value for v, 21,000. Pi, which is 3.14 roughly. Rho. Now here you have to use the density of the vapor. Okay, I forgot to put this raw V. Okay, density of the vapor, and that's about 3.68. And the value for operating, oops, we have one more trouble, and that is the unit for velocity is not consistent with the density units. See how it's in meters? We got to convert this to meters. So 3.5, when you convert it into meter, what is the conversion factor? If you look at in the back of the textbook, if you don't remember it. 3.28 feet per meter. So you divide 3.5 by 3.28, you'll get about 1 point something.
And then the seconds.
1.07 meter per second. And then you could put it over here, 1.07. You see what I did? I just converted from to meters per second and then put it over there. That's it. You got your d square. That's true. That's true. Let me write that. Let me write that properly. Okay. Since I've made so many mistakes, let me write that properly. So you got 4 times 21,000. Now this is in kg per hour. So we have to put the 3600 over here. Times 3.14 times 3. Density 3.68 times 1.07. Right? Okay. Thank you so much. Thank you so much. And so you get your d square from there. So value for d square comes out to be something like, I don't know how many meters square. 1.88. So then you calculate your value for d, which is square root of 1.88. 1.88, 1.4, 1.35, 1.37. Okay. Fantastic. You just designed a tower. So from experience, I can tell you that that's about correct. So if you have 1 meter, yeah, you have somewhere between 1 meter and 1.5 meter, you need about 24-inch spacing, 2 feet spacing. Try to imagine this. Try to imagine this. You got a meter stick, or you've seen a yard stick. So meter is slightly above yard, slightly more than yard. So think about a yardstick and maybe 1.5 yardstick. That's exactly right. So 1.5 yardstick, wide column, on circular diameter, and then how will you space the 2 trays? 2 feet is roughly about correct. Roughly about correct. Okay. So you see how you can design the columns this way? Okay. Now what I'm going to do is I'm going to introduce the next topic. This is called the enthalpy concentration method. In this method, we use another kind of equilibrium diagram that I haven't talked about. This equilibrium diagram takes into account enthalpy or energy of the system. When we did McCabe-Thiele, we talked about, we say, let's ignore the difference in latent heat of vaporization of A and B, and we assume constant molality, right? Then we also say, okay, let's forget about the differences in CPL, no sensible heat. And so as a result, we got this constant molar overflow. But in reality, that's not true, okay? So we need a different kind of a method, a different kind of a system to draw these, to do these constructions. So there's a method called enthalpy concentration method, or the Ponkin-Savret method. If you go to other textbooks, you will see that name, Ponkin-Savret method. Just don't get confused. What you do in this method is you do enthalpy balances along each tray. Across each tray, you're doing enthalpy balance, right? Because across each tray, the enthalpy lost by the liquid stream will be equal to the enthalpy gained by the vapor stream. That's the best way to kind of make a balance, heat balance. So it accounts for differences in latent heat, heat of solution in mixing. So for example, some amount of toluene dissolves into this mixture, there's going to be some heat generated, okay, heat of solution. And then it takes into account the heat of CP. So CP, you guys remember CP, MCP delta T? Raising it from some low temperature to the boiling temperature, so it takes care of that. For this particular method, what I will do is I'll spend the rest of the lecture talking about this specific diagram, because we need to understand and learn correctly how to use this particular diagram. So here I show you two diagrams. Okay, don't get confused. Let's start with the easy one, which is for the benzene toluene system. So what you do is you plot mole fractions of the lighter component. So in this case, in case of benzene and toluene, benzene is the lighter component, right? You plot the mole fractions. The mole fractions can either be XA or YA, okay? So I'll tell you why. It goes from 0 to 1.0. And on the y-axis, you plot the enthalpy of the mixture. It can be capital H or small h. Okay, that's interesting. You remember when we did McCabe-Thiele diagram, or the isobaric curves, we had a diagram that looked like this. There was temperature on the y-axis, and then mole fraction, x and y's on the x-axis, and then we had two curves that look like this, right? We had this curve was called the dew point curve, bubble point curve. Similarly, you have two curves here. The top curve is one for the saturated vapor. Okay, saturated vapor means vapor in its vapor at its boiling point. And then the bottom curve, which is the small h, it is one for the saturated liquid. Saturated liquid means liquid mixture at its boiling point. This capital H, whenever you read any points off of that, or you are trying to locate a point on this curve, you always use YA values, because this corresponds to the vapor phase. The bottom curve, which is a small h, always you use the x value or read the x value, because this corresponds to the saturated liquid phase. Okay, so this way you have two curves. One is the saturated vapor curve, one is the saturated liquid curve, capital H and small h's, both representing enthalpy of the vapor and the liquid phases. Okay. Now let's look at another system right over here. I believe this is one for the heptane. The units are slightly different. In the first one, it is kilojoule per kg mole of the mixture. here look at the units. BTU per pound mole times 10 raised to minus 3. Okay, BTU per pound mole, that's a unique unit. But what does this 10 raised to minus 3 indicate? So for example, if I read a value, let's say this value, 30. So is it 3 times 10 raised to minus 3 BTU per pound mole? Or is it 3 times 10 raised to 3 BTU per pound mole? Yeah, 10 to the third. Not 10 raised to minus 3. It's 30 times 10 raised to 3 BTU per pound mole. Okay? Please be very careful. Okay, this graph, the reason why I took it second is that there are more curves over here. See, here's the saturated liquid curve, and here's the saturated vapor curve. Okay? Anytime, let's say you have a system at equilibrium, if you have X as the composition of benzene in the liquid, what is the corresponding equilibrium composition in the vapor phase? How do we denote those? We use tie lines. So let's say, so in this case, here, 0.41, remember we are always reading liquid. Okay, so for example, if we know that the composition of the liquid is 0.41 in terms of benzene, then we project it to the saturated liquid case, liquid line. Then we follow the tie line, and then wherever the tie line intersects the saturated vapor curve, we read the y-axis, and hence your y is going to be 0.62. Yes.
How do you know the angle of the tie line?
Angle of the tie line, very good. Just one moment, I'll go there in just a minute. So the reason why I chose this first diagram to be very simple and just one tie line is so that you see the how to read it. Now let's go to the complex case. Okay, how do you read the tie line? Typically you can plot the tie lines, and I'll show you, but if the tie lines are given, so sometimes the tie lines will be given, so these are tie lines. Okay, so these are tie lines. Sometimes you have to, let's say you have a point like here and you have to draw a tie line. Well, you gotta estimate a slope. You gotta estimate a slope that is similar to this one and this one, or somewhere in between the two, and then try to okay, then you try to draw a line with a slope in somewhere in between. Okay, same thing over here. So let's say this point, if you know this point, you try to draw a tie line that has a slope very close to, you know, either of the lines on the two sides. Okay, these are also called, since they correspond to the same temperature. You remember on here what you did was you located a temperature. I'm sorry, let me change the color. Okay, you located a temperature here or on this axis, and then you draw a line. Your tie lines were very, very flat. In this case, the tie lines, and remember the intersection points, this was X, this was the Y, corresponding in equilibrium. Here, the tie lines are not flat. They have a curve. Okay, that's the difference. I'm sorry, this one. So these two are in equilibrium. Now, let me address another concern. Okay, so let's say you plot, what you do is you plot two diagrams, okay, with the same scale, 0 to 1, 0 to 1. Here's the enthalpies, and here's the Y versus X. Okay, so here you have, in the enthalpy diagram, you have two curves, one corresponding to the capital H, one corresponding to the small h. On the McCabe-Thiele diagram, what does the McCabe-Thiele diagram look like? There's the reference line, and then you have this equilibrium line, right? Okay. For example, you want to locate, you know your x value, you want to draw tie lines, okay, on this curve. How do you draw it? Let me change the color. Okay, how do you draw it? So what you would do is for every point, or you can choose some points. So let's say we were drawing a tie line corresponding to this point. That point is actually a line on the enthalpy concentration curve. It's only a point on the McCabe field curve, field diagram, but it's a line, it's a tie line. And how do you do that? Okay. So this point has an x value, right? So what you do is to locate that x value, you just project it down to the small h curve, because that's liquid phase. Now, for the y value, you have to draw a horizontal line, let it intersect the reference line, and you drop that to the capital H curve, and you'll get the y value there. When you join these 2 points on the enthalpy concentration diagram, that's how you get the tie line. Okay? But for this particular class, I won't have you do this. Okay? I will give you all the tie line data and everything. What I want you to focus on is how to use the enthalpy concentration method. Okay? Let me just do one more point, exercise with one more point, and then, so let's say we were plotting this one, okay? X-axis, so you just horizontally project it down, so you get your x, but then for the y, you draw it across, and then drop it off to the capital H. If you keep drawing this, you will see that the tie line is kind of vertical over here on the left hand side, and it will start taking some slopes, but then it will also become vertical over here. Okay. All right. Okay. How do you construct an enthalpy concentration diagram? What we looked at is what do they look like, how to read them. That's where I want you to focus on mainly. I don't want you to focus on how to construct them too much. Maybe for your homework you might have to do that. But you have the Excel file online and you can look at it and how to do it. But I want you to focus on how to read it the best, okay? What do you need? You need Cp, which is a function of temperature, pressure, and composition. Cp of the liquid, okay? So Cpl. You need the Cp of the gas phase or vapor phase. So that's also a function of temperature, pressure, and composition. And then you need the heat of solution, which is a function of the temperature and the composition. You need latent heat of vaporization. That latent heat is again a function of temperature, pressure, and composition. And you need boiling points. Boiling point is a function of composition and the pressure. You see how much data you need? This data you can find from the handbooks for the chemistry. CRC handbook chemistry, NIST chemistry webbook. All this data, you can find it online on the NIST chemistry webbook. Or you can go to CRC or Perry's and you'll find this data. You get that data, then you can construct the H curve, the small h, the liquid enthalpy. What you are doing here really is 2 things. You're adding three things. You're considering the enthalpy of that liquid for the benzenes. So for example, we are considering benzene toluene system. So this would be the benzene. This is the enthalpy of the benzene. This is the enthalpy of the toluene. And this is the heat of mixing them. Make sense? That's how you calculate the enthalpy of the liquid. Similarly, how do you calculate the enthalpy of the vapor line? Well, you take the composition of benzene, add the latent heat of vaporization, and then CPY, so that is the latent heat, the heat capacity of the vapor phase of benzene times whatever the temperature difference you're creating. Okay, so this is the enthalpy of benzene vapor. This is the liquid. And this second term here is the enthalpy of toluene in vapor. Typically, this little, minimum, I shouldn't say zero, minimum enthalpy or heat of mixing of gases. You'll never see that reported. Usually it's the mixing of the liquids, because molecular collisions are higher when you do it in liquid scale, whereas in gas phase molecular collisions are less dense, right? Okay, now then comes how do you calculate the latent heat of vaporization. The latent heat of vaporization, again, that's a tricky part, because that's a function of temperature. Okay, so latent heat of vaporization again is a tricky one to calculate. So you have to take CPA and CPYA. So these are the MCP delta T, the sensible heats in the liquid phase, sensible heat in the vapor phase, and you're adding that. See how complex the calculations become? Calculations but look at the amount of heats and enthalpies it's considering. How extensive this method is compared to the McCabe field. The McCabe field is really a back of the envelope calculation. This is not. And when you take into account many different things, that calculations become really difficult. And hence, you can find the enthalpy value. Your first aim should be trying to find these enthalpy values from journal articles, Perry's handbook. Even this book has some enthalpy, small h and capital H is given. There are so many other textbooks. Try to look for that data when you're doing design. Now, the hi-fi calculators, the $60,000, $100,000 calculators, Aspen, ChemCAD, what you're using, those calculators, they do it for you. Okay, they generate this data for you. You guys are already doing, you're estimating free energy and activity coefficients and everything in your Thermo 2 class. All that, you can start from the basics and try to predict molecular properties at different temperatures, pressures, mole fractions, everything, theoretically. And hence, when you use those programs, hi-fi calculators, you always still have to go back to the lab, do a pilot scale experiment, see if it is correct or how accurate it is, and give corrections to it, okay? Before you do a full-scale plan. Okay, look at this data set. Here's how construction of, I'm probably explaining the construction of enthalpy concentration data. You go look for these data sets. Okay, when you're constructing these, that's what you go look for. And these are the values calculated, and hence you can build your own data set. So you can look at heptane ethylbenzene. That's an example that I uploaded online. So you can see how I collected those these data and created my own enthalpy concentration data curve. So I uploaded that Excel file. Okay. All right. Thank you so much. And so basically today we looked at two main things, very important things. One is how to calculate the diameter of the tower, and second thing is how to interpret enthalpy concentration. All right. Next class, what we'll do is I'll bring in big charts for you guys to plot this enthalpy concentration data on, so we can do some hands-on design.